Lesson 3.2, Polynomial Functions of Higher Degree. In this lesson, we'll look at transformations of polynomial functions, we'll use the leading coefficient test to determine end behavior, and we'll find real zeros and use them as sketching aids. To find the graph of a polynomial function, you would consider a graph as continuous if the graph has no breaks, holes, sharp turns, or gaps. In this first graph, this would be a transformation of a cubic function. And it's a continuous curve. It has a peak and like a high point and a low point. From left to right, it continues on. So yes, this is a continuous function. Now that second function would be a piecewise looking graph. As you can tell from left to right, there are different things happening for your inputs. Plus there's kind of a break from left to right. Therefore, no, it is not a continuous function. Now the next graph is just some random polynomial. We're not even exactly sure how many zeros it could possibly have. So we'll just call this one a polynomial. There are curves from left to right. It has several maximums, a couple of minimums, but there are no breaks in the graph. Therefore, yes, this one is continuous. And then last but not least, this last graph would also be a piecewise. It looks like it could maybe be an absolute value, but from left to right, it isn't stretching the same amount. Therefore, it does look like it's considered piecewise. And this location right here, where it goes from decreasing to increasing, would be considered a sharp turn. Therefore, it is not continuous. The leading coefficient test describes end behavior. The leading coefficient is just the first term when it's written in order from highest to lowest. And that can tell you some things about the left-hand side and the right-hand side of your graph. Now, when you're looking at your end behavior, you want to look at, like I said, that leading coefficient, the lead term. Now, the lead term is either going to have a polynomial or a degree that is odd or a degree that is even. When a degree is odd, like ax cubed, for example, that's an odd exponent. Looking at your lead coefficient can tell you some things about your end behavior. If a is positive on the left side of your graph, it falls or goes towards negative infinity. On the right side of your graph, it rises or goes towards positive infinity. If your leading coefficient, though, changes from positive to negative, that changes as well. So now on the left-hand side of the graph, as x gets smaller, the y value rises on the left, so it gets bigger, and on the left-hand side, it falls. I guess I actually wrote that in the wrong spot over here. Sorry, I'll change that for you guys. So it'll be your output value on the on the right, and then your output value on the left, falls and rises. There we go. So that's when you have an odd exponent and your lead coefficient is either positive or negative. When your exponent is even, like a quadratic or even what's called a quartic function, so we'll say just like ax squared, we know that both of our arrows always point in the same direction. Now, if your lead coefficient is positive, notice both arrows point up and your graph rises on the left and on the right. And then if your a coefficient is negative, we know that our graphs always point to negative infinity, so it goes towards negative infinity in both directions. It falls on the left and falls on the right. So what you want to look for, you want to look for the degree of the function first, describe it as odd or even, and then look for your a value. Is a positive or negative? And we describe our end behavior like up above. Let's try a couple of examples. Describe the left-hand and right-hand behavior of the graph of each function. So without actually seeing the graph, we can describe what the arrows would do if we were to sketch it. For the first example, f of x equals negative x cubed plus 4x. It's written in this standard form, and this is its highest polynomial. Because of that, look at the degree of the function. N equals 3. So n is an odd number, therefore it's an odd polynomial. Now look at your a value. Is it positive or negative? Taking a look at that negative sign out in front, we would know that a is less than 0. Now you just need those two things. Looking up above, we should be able to describe the left-hand and right-hand behavior. So the left-hand behavior on the left-hand side of the graph, if you have an odd function and a is negative, your graph rises. So you literally just have to say it rises. On the right-hand side, or the right-hand behavior on the graph, as x gets bigger, the graph actually falls. And that's describing n behavior for left hand and right hand, just using what we know about the degree of the function and the value for the lead coefficient. Let's try the next example. Now taking a look at this function in standard form, I notice we have x to the 4th power. That's a quartic function, and 4 is an even number. Therefore, the degree of the polynomial is even. And now taking a look at the number out in front, that a value, technically it's not written there, so we would default it to 1, although you can't really tell I just wrote that in there. Let's try that again. There's a 1. A is now greater than 0. So think of anything that you've graphed, like a quadratic or anything that would be an even number like that. If a is positive, no matter what direction you go on the left or the right, we would know that both times the graph would rise. The arrows would point up towards positive infinity for your output. And so you would just say rises for both of them. All right, one more. H of x equals x to the 5th minus 1x. This is called a quintic function, and the biggest exponent is 5, which is odd. And now if you look at the number out in front, technically it's just plain 1. Now we would say a is greater than 0. So following the indication up above, on the left-hand side, as x goes towards negative infinity, the graph would do the same thing. The graph would also fall. And then on the right-hand side of the graph, you maybe have a couple maximums and minimums, but as x gets bigger to the right, the output does the same thing. It rises. So part of your homework today will be simply to use this leading coefficient test to describe n behavior for different functions. No lesson these days would be complete without finding zeros of a polynomial. Now, when you're asked to find zeros, there are lots of things that are equivalent to doing that process. You can say that your value is a zero of the function. You can also say that you have a solution to the function. If you have your variable in parentheses, that would be a factor of the polynomial function. And then if you write it as an ordered pair, ultimately, every time we solve, we're looking for the x-intercepts for any of your polynomial functions. And just like we've talked about many times before, to determine your zeros, always set the equation equal to 0. When we have higher ordered polynomials, you're going to often find a common factor. You'd want to take a look at factoring that out first. Once you've factored everything that you possibly can, apply the zero product property. Sometimes you'll have just 2 or 3 zeros, but you could have 4 or 5. Another thing you'll look at, when we've seen those kind of unique looking graphs in the first couple of slides, they have several different peaks and valleys or maximums and minimums for their functions, and those are known as turning points. And a turning point is how many times a function can turn from increasing to decreasing, or the other way around. So it's like finding maximums and minimums. How many times can a graph do that? The formula to get that would be to take the degree of your function, the biggest exponent, and then all you have to do is subtract 1 from it. And that will tell you how many possible maximums and minimums that graph can have. Find all real zeros of f of x equals negative 2 x to the 4th plus 2x squared. Then determine the maximum possible number of turning points of the graph of the function. So if we take a look at finding real zeros first, Let's take our polynomial, negative 2x to the fourth plus 2x squared, and set it equal to 0. Now, the key here is the biggest exponent means you could have up to 4 real solutions or 4 real zeros. So we could have 4 different answers when we're done, but it's not always guaranteed to be the case. To figure out your zeros, again, we set it equal to 0 and factor. Take a look at negative 2x to the fourth and and 2x squared. We could actually factor a negative 2x squared out of both of them. And if we took negative 2x squared out of negative 2x to the fourth, we'd have x squared. If we take negative 2x squared out of positive 2x squared, we'd have minus 1 equals 0. Now the negative 2x squared on the outside doesn't factor any further, but the x squared minus 1 actually splits part into a difference of 2 perfect squares, x plus 1 and x minus 1. And then we have that negative 2x squared out in front. Once you have it factored, we apply what we call the zero product property. Set this equal to 0. And if you divide by negative 2, we get x squared equals 0. When you square root 0, you only get one solution for that, so x equals 0. If we have x plus 1, remember up above, that's called a factor. So to get x by itself, move 1 to the other side. We get x equals negative 1. And then x minus 1, another factor, add 1, and we get x equals positive 1. So we actually have 1, 2, 3 different zeros for our polynomial function. And remember up above, we said there were up to 4 real zeros. So let's talk about what that means in an equation. Sometimes when you have a polynomial, you have what's known as repeated zeros. And that's actually what happened up above. If you have a factor that has an exponent where it doesn't change the value of your answer, it's known as a repeated zero. And then your solution will have a multiplicity. So what we're looking at, we're not really even worried so much about k equals odd and k equals even. Let's take a look at those 2 examples down below. If we have f of x equals x squared minus 6x plus 9, that's quadratic. And we know that it should have 2 zeros. But if we set it equal to 0 and we factor, 2 numbers that multiply to get 9 but add to get negative 6 are negative 3 and negative 3. Which means only one of them, or there's only going to be one solution because of that. If you have x minus 3 squared equals 0, x would equal plane 3. It wouldn't equal 3 twice, so if we put our point at 3, but it counts for 2 of the solutions because it was quadratic, we would say that this is a double zero, or a repeated zero. And then it would have a multiplicity of 2, because it stands for 2 of all of the quadratic solutions for that function. This also means it's the vertex for the quadratic function. So you would just draw a curve that goes down, touches that at that point, and goes back up again. Now the next example is a cubic function. Notice you have a 3 over here as the exponent. You could FOIL it out and get a big polynomial that has an x to the third in it. However, you wouldn't need that for graphing purposes. If you have x plus 2 to the third power, that means if you set it equal to 0, and you take the cubed root of each side, you just get x plus 2 equals 0. You wouldn't get anything else. And when you subtract 2, you'd get x equals negative 2. So it should cross the x-axis at negative 2. Now the unique thing with that is that it doesn't stand for 2 solutions, it stands for 3. So this would be what's called a triple zero, also known as a repeated zero. And it has a multiplicity of 3 because it represents 3 of the solutions. Now back in chapter 2, we had a parent function that was cubic. And it kind of just looked like it was almost a line, but then it kind of curved through that point on the x-axis. And that's what this graph will do as well. It'll come up, kind of curve, and then go back to increasing again. And that's kind of a basic rough sketch of what a repeated zero would look like. So your assignment for 3.2 day 1 is on page 261. We'll do 20 through 26, the evens. And that's looking at the graph and simply describing, or looking at the equation, and simply deciding what the left and right hand behaviors are. For 34, 36, 39, and 42, do parts A through C on each of them. You don't have to do part D.